Having successfully broken down our IP address into a binary string, writing the subnet mask out is really simple in this case because anytime that you have an octet represented by the decimal 255, you know that at the binary level, every bit is set to 1. If you add up 128, 64, 32, 16, 8421, you get 255 every single time you do it. Doesn't matter how many times you do it. Also 0, that's pretty simple because that's setting every bit to 0, so when you add them up we have 0. So here, very clear-cut subnet mask of 255, 255, 255, 0, but why did we do this to begin with? Why do we need to write the subnet mask out? Well, the subnet mask tells us where the network bits and the host bits are in the IP address. The network bits are indicated by a 1 in the subnet mask and the host bits by 0. Now the first 24 bits of this particular IP address are the network portion of the address. And when we add those bits up, we get 192.168.10. We can really do that without adding them back up because the line here is so clear cut as to where the subnet mask ends. So we could pretty much look at that and say, okay, 192.168.1, that is the network portion of the address, and you would just go ahead and put a 0 for that fourth octet. When you tack on the subnet mask, the network that host resides on is 192.168.10, 255, 255, 255, 0. That's it. Now, you could certainly look at this example, and you probably are thinking, hey, this was pretty simple. I didn't need to write that stuff out. I could look at this and say, okay, if there's a /24 mask, I know that it's on the network 192.168.10. I know where the network bits are. This is true, and it'll be great that you can do some of these by sight. But when the subnet mask isn't so cleanly ending at 8, 16, or 24, I strongly suggest you write the subnet mask out. We'll have some examples of those in the subnetting section, certainly, but I wanted to show you a basic example first just to get you comfortable with it, and I'm sure now you are comfortable with it. Now about that /24 bit, you can express the mask using prefix notation, which is a fancy way of saying I'm going to put a slash there and then follow it by the number of consecutive ones in the mask. And in this case, that is /24. So either expression of this subnet mask is acceptable. And you got to watch that on the exam because they might throw some mass at you in dotted decimal, others in prefix notation. Maybe a question has both. So you got to be ready for that. But again, and you can see where prefix notation is a lot easier to work with, especially if you're reading addresses out loud in a meeting. Instead of continually saying 255, 255, 255, 255, you could just say /32. And that's what most people do. And of course, it fits a lot easier on a network map, as you're seeing in this course already and will continue to see. So just a taste of binary conversion there, more to come, but I just want to get you over that mental hump if you had that about being nervous about doing binary conversions. Because once you get practice in, you'll be doing it just as easy as you would add 2 plus 2 in decimal. Now let's talk about these IP address classes a bit. We don't talk about things from September 1981 in networking very often, but these address classes were defined then, and they are still around. They were defined in Request for Comments 791, and these are technical proposals and or documentation. And I will admit they are not always the most exciting reading in the world. But occasionally, especially when you're going through these routing protocols for the first time and you get comfortable with them, maybe you want to look up their RFCs. You can find them very quickly online and just peruse them. Like I said, they're not really written in a friendly style on occasion, and I'm being kind. But go ahead and dig into them. I just want you to know what an RFC is to begin with, because occasionally you will see address classes or protocols referred to by an RFC number in Cisco documentation, one in particular which is coming up in about 2 minutes. But about these address classes, let's get back to that. The class that an address belongs to is indicated by the first number, first octet. And you got to have these address classes down cold. A little memorization, you may be in order right now, but they become second nature to you. But you've got to be ready to identify the class that a given address belongs to on test day. You've got to be ready to do that. Now these are the classes from 1 through 255, the classes and addresses that can be assigned to network hosts. We have 3 classes. Class A, the first number is in the range 1 through 126. Class B, the first number is in the range 128 through 191. Class C, that first number is in the range 192 through 223. And you may be saying, Chris, you left a few out. Well, I didn't leave a few out, but we have some numbers that are reserved that can't be assigned to hosts. And the first one, loopbacks, 127. Any address that belongs to 127 is a loopback address. Please note these are reserved for host loopback interfaces, not Cisco router loopback interfaces. And these are interfaces, again, we'll be creating later. And if we try to put an address on a Cisco router loopback that starts with 127, the router is going to bounce it right back at you and say you can't do that. So please keep that in mind. It's the loopback range begins with 127, but they're for host loopbacks, not Cisco router loopbacks. Class D, 224 through 239 will be the first number for those. That's reserved for multicasting. Multicasting is our middle ground between a unicast and a broadcast. We know what a broadcast is. That's destined for everybody. A unicast, as you'd get from the name, is destined for one particular individual. We have a middle ground called multicasting, where a message is sent to members of a certain group, and there will be multiple members. So we're not just sending it to one person, and we're not just sending it to everybody. It's that middle ground. And OSPF and EIGRP, two routing protocols you'll be introduced to. As a matter of fact, RIP version 2, these all use an address from that range to do its work. We'll see that in action. But Class D, 224 through 239 is the first octet there. Class E, 240 through 255, reserved for future use is the official phrase you usually see with that range, and occasionally referred to as experimental addresses. And they don't want you to know what experiments we're doing with those addresses. Matter of fact, it's so secret they haven't even told me. But those are your Class E addresses. Now, in turn, each of those public address classes we just looked at, A, B, and C, each one has its own default network mask, its own default number of network bits, and its own default number of host bits. This information will become second nature to you, but memorizing it for right now is an excellent idea. Class A, the default network mask is 255.0.0.0. We know now what that means as far as the network bits and the host bits are. The first 8 bits in that address are set to 1, so we know we've got 8 network bits, and then everything else is a host bit, 24 host bits. Class B, our network mask is 255.255.0.0, 16 network bits, 16 host bits. Class C, you know what that's going to be. Network mask of 255.255.255.0, 24 network bits, and 8 host bits. Now, coming up next, we're going to talk about these private address classes. These are subsets, if you will, of the address classes we just looked at. And you've probably noticed this. You know, we have hosts at different sites that use similar IP addresses or the same IP addresses. We're going to talk about why that's possible and what today's challenges are with those addresses. That's coming up next.